All right, welcome back. So, where are we? Where were we? We last finished up the setup, and we got our logical device created and the queue families, indices, and the queue. And now we're moving on to the Windows surface. So, since Vulkan is a platform agnostic API, it cannot interface directly with the Windows system on its own. To establish the connection between Vulkan and the Windows system, to present results on the screen, we need to use the WSI extensions, Windows System Extensions. In this chapter, we'll discuss the first one, which is VK KHR surface, which we saw that before. It exposes the VK surface KHR object and represents an abstract type of surface to present rendered images to. The surface in our program will be backed by the window that we've already opened with GLFW. The VKKHR surface extension is an instance level extension, and we've already enabled it because it's included in the list returned by GLFW get required instance extensions. That's why we've seen it before. The list also includes some other WSI extensions that we'll use in the next couple of chapters. The Windows surface needs to be created right after the instance creation because it can actually influence the physical device selection. Oh, interesting. The reason we postponed this is because Windows surfaces are part of the larger topic of render targets and presentation, for which the explanation would have cluttered the basic setup. That's fair enough. It should also be noted that the Windows surfaces are an entirely optional component of Vulkan if you need to do off-screen rendering. I don't know why I'd ever want to do that. Vulkan allows you to do that without hacks like creating an invisible window necessary for OpenGL. Ooh, shots fired. Windows surface creation. Start by adding a surface class member right below the debug callback. Wonder why they want us to do it right below. Okie dokie. Back up to our abstract. Okay, this is our debug message callback. So let's throw it here. Let me just also move my mic up a tad. There you go. Alright, so although the VK surface object and its usage is platform agnostic, its creation isn't because it depends on the Windows system details. For example, it needs the HWND and HModule handles in Windows. Therefore, there is a platform-specific addition to the extension, which on Windows is called VK. I don't care about Win32, well, not yet anyway. And it is automatically included in the list from the GLFW extensions. Okay, I will demonstrate how this platform-specific extension can be used to create a surface on Windows, but we won't actually use it in this tutorial. It doesn't make any sense to use a library like GLFW and then proceed to use platform-specific code anyway. GLFW actually has the GLFW create Windows surface function that handles the platform differences for us. Yes, thank you, GLFW. Still, it is good to see how it works behind the scenes. Yes, that's great. Okay, to access native platform functions, we need to update the included at the top. Okay. So we want to now have use platform Win32. No, I don't think we do. We've already got included Vulkan, and we've included that. Expose native Win32 and blah blah blah. Oh, this is the bit we're actually going to skip because we're not more Windows. So because the Windows surface in Vulkan object comes with blah blah blah, needs to be filled with parameters. Okay. Where I think we can just omit all that kind of stuff. I mean, it is good to know, but I actually won't be able to do it on here anyway. I might come back to that and look at doing it specific to Linux. After the set is created, blah 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 blah. Okay, the process is similar for other platforms like Linux, where VK create XCB surface KHR takes the XCB connection and window to create details with X11. Okay, The GLFW create window service function performs exactly this operation with a different implementation for each platform. We'll now integrate it into our program. This is the bit we care about. Add a function create surface to be called from init Vulkan right after instance creation and debug set up debug messenger. All right, create surface. I could probably just squeeze this over here. Let's create the function prototype. Let's do it here. Void create surface. It's almost certainly going to take in our pointer to app. Hopefully I'm not being biased by stating that originally anyway. Create instance. Let's just scooch down to where that's defined and put this right below that. Okay, so our create surface is going to be called in init Vulkan right after the create instance and before. Was that? Yeah. And the debug setup. Okay. P-app. Ooh, that's the wrong case. There you go. Okay. And then in the create surface function, the GLW call takes simple parameters instead of a struct, which makes the implementation of the function very straightforward. Grand. Okay. Woi. Fast fingers today. Just inaccurate as well. Okay, GLW create window surface takes in our instance, our window object, and a null pointer and a surface. What's the window? Oh, did we create that at the top? Okay. So if glfw create window surface takes in our pointer to app, instance, and our window, and a null pointer, and a pointer to surface. Now, let's just check something in a second. If that doesn't equal VK success, then I don't know what does. Sorry. Then we want to exit basically. And we're going to say, we've got 4, so let's go 5. I think in the next video I'm going to do the cleanup for abstracting some of these. No, I won't abstract these into files yet. It's pretty early days, but I will create a proper error system. Well, a proper simple error system. So we don't need to keep doing, we don't have to keep saying print something and then give me a really poor semantic number of exit. Okay, so fail to create window surface. All right, so do we have a window and a surface on our app? Window and a surface? We do indeed. All right, there we go. The parameters for the VK instance GLFW window pointer, custom allocators, and pointer to VK surface KHR variable. All right, yes. Yeah, all right. So it simply passes through the VK result. Yep, that's fine. GLFW doesn't offer a special function for destroying the surface, but that can be easily done to the original API. Okay, so we destroy the VK surface in cleanup. Let's do it here. Let's do it right before we destroy the instance. VK destroy surface KHR. Passing in our instance and also our surface, and then a null pointer for whatever the hell reason. Grand. Make sure that the surface is destroyed before the instance. Okay. Then let me just quickly try and compile this. And we have got an error. So this is expecting, what is it? Line 227. First use the function. Did you mean app? I don't know, did I? Don't think I did. Note each uncleared identifier is reported only once. Okay. And line 227. Let's go find line 227. Yes, I did. I think I probably meant this actually. That makes more sense. Alright, let's just pop it open. Yeah, everything seems to be cleaned up, no errors. Excellent. Now, querying for presentation support. Although the Vulkan implementation may support Windows system integration, that does not mean that every device in the system supports it. Therefore, we need to extend is device suitable to ensure, this will be in our rating, to ensure the device can present images to the surface we created. Since the presentation is the queue specific feature, the problem is actually about finding a queue family that supports presenting to the surface we created. Alright, it's actually possible that the queue family supporting drawing commands and the ones supporting presentations do not overlap. Okay, therefore we have to take into account that there could be a distinct presentation queue for modifying the queue family indices, by modifying the queue family indices structure. Okay, so that's it. We had this structure, or the struct, that we put our graphics family indices on, and then its presence or not presence in absence of having an optional type. So now we have the presentation family, and the is complete will just have a specific one for graphics and a specific one for present. Okay, so let's add that into our struct. And let me just copy this and say present and is present family set. Excellent. Hopefully that lack of, yeah, that's fine. I was gonna say, if we don't actually specify those when we create the struct, hopefully it doesn't give us any kind of error. Okay, so in our rate device suitability function, or perhaps not in here. Oh no, in here. Find queue families, queue family indices. So in this find queue families function is where we do setting up our graphics. Oh wait, that's not the function. This is the function. Here we're getting our graphics specific one. Yep, here it is. So if we have graphics support, we then add it to our indices struct. So we also need to do something like, well, actually something like this, but it'll be a different one of these. Let's just say present for now, and then we'll add that to our indices like so. Present family, and then is present family set will be true. But getting ahead of myself. Okay, next we'll modify the queue find queue families. We're already doing it. To look for the queue family that has the capability of presenting to our Windows surface. The function to check for this is vkget physical device surface support KHR, which I am going to copy because early morning I am likely to fail to do that properly. Okay, so this is actually not what we're trying to do. We need to do a vk bool and present support initially equal to false. Then we do that, pass in our device. And a surface. Okay. Oh, actually no, this will happen in there. But we'll come back to that. That'll happen within our loop, but let's come back to that. we have to say surface, okay, and present support. So I think this is where we want to do that. Similarly, that, so I can probably get rid of this. If it's actually just going to be this. If that is true, then we set the Q into the family present, or the present family to the I, whichever is the iteration number we're in, the Q family indices, and then set that to true. But now this function requires us to pass in the surface, which is a bit of a bummer, because I don't really, that is a real bummer. We're gonna pass a copy to it. Now then, here's an interesting thing about C. Do we wanna, we have to decide if we wanna pass in the copy or pass in a reference. So pass by reference or pass by value. This is one of life's greatest mysteries. It's not really, is it? Not at all. When we're calling find Q families, we have access. Oh, hang on. Oh no, I just added that myself. I should have slept for longer. So when we're calling find Q families, here, what do we have access to in this function? Do we have our app? We do. So let's also pass in p-app surface. And then when we call that again further down, let's also modify the prototype. Looks like I've already decided we're passing by value. So we're going to make a copy of it. Here's another call to that, and let's pass in our p-app surface. Oh, that's my stomach rumbling. And yet another call to it where we've only got the device. Oh, rough. In our rate device suitability, we don't have our surface. Nuts. That means I gotta pass it in here as well. Oh, that does suck. All right, p-app. So we've got to pass in like two levels in, two function levels. We've got to pass a Vigo surface just so a child function can have access to it. God damn, that's really unfortunate. Okay. All right. Well, now we have presentation. Now we have actual surface. Ugh. Let's just check if I haven't made a mistake. Looks like I have. Oh, I need to change the prototype for our rate function, I believe. Excuse me. VK surface. Yep, I think that's fine. Yeah, okay, that's it. Right, now we have our surface. So we then have our present family index. Note that it's very likely that this ends up being the same Q family after all. But throughout the program, we will treat them as if they are separate queues for a uniform approach. That makes sense. I like that idea. Nevertheless, you can add logic to explicitly prefer the physical device that supports drawing and presentation in the same queue for improved performance. Ooh, oh, okay. Well, let's actually make a note of that. No. To improve performance, we could favor Q families that have both graphics and present support. Which means no. So the returned indices. Oh, hang on, let's just say we could check the returned indices, and if they are the same, increase the score. That would make sense to do, I think. So if both the indices were the same, we'll agree, this is the one, this is the device to pick. If everything else checks out, nothing else sets it to 0. Perfect. I think also another thing to make note of is that if it doesn't support geometry shaders, we shouldn't set this to 0, we should actually just return 0. Just exit out early, because we don't want to override it with some of the fancy stuff that we come up with. So we could end up with a graphics card that has really good other things that we care about, but doesn't support geometry shaders. That would be terrible. So yeah, let's just return 0 on that. Okay, cool. And also don't have so many spaces. Stop it. Okay. Done. Creating the presentation queue. The one thing that remains is modifying the logical device creation procedure to create the presentation queue and retrieve the VKQ handle. In a member variable for the handle, add a member variable for the handle. Similarly, up here we have our VKQ for graphics. So let's do VKQ for present. Next, we need to add multiple VK device queue create info structures. VK device queue infrastructure. To create a queue from both families. An elegant way to do this is to create a set of all unique queue families that are necessary for the required queues. Indices queue, find queue families. Yep, already kind of got that. Okay. So we create a vector or a list of VKQ device create infos. Device queue create infos. And then we go through those unique queue families. Oh, unique queue families. Indices graphics family value. Oh, we create a set. That's cool. I don't know if we have sets in C. Actually, I don't think we do. We have to create one if we really wanted to. Then set the queue priorities like we did here. And then for each unique queue family, create a struct. That is a pretty elegant way of doing it. It sure is. Yeah. Modify VK device create info to point to the vector. What's our inelegant solution for now? Since we can always make things look pretty and performant once it works. Getting it to work is the important thing. Let's just create a function for our graphics queue and one for our present queue. I think that would be the way I'm going to do it. But let me just quickly read on. So they basically do the same thing. It's just the queue priority, and well, that's always the same. And the queue family, that index that changes. So once they've got that create info, they just do the same thing that we do, which is use it in where do they use it? Oh, down here in the creation of the device. Oh, hang on. Are we creating multiple devices? I don't think we are, no. This is interesting. Let's have a look at this function. vk get device queue. Let's go to the docs and find vk get device queue. So it takes a single index and a queue index. It's a shame there's no actual description on the function. That would have been nice. Get a queue handle for a device. Oh, okay. Queue family indices. Oh, right. Okay, so we're passing in the specific queue family that we care about, and that is what gets updated. I believe. This is our graphics queue. What's that? Okay, so we want to do the same thing. Yeah, let's just do it in its own little function. All right. Let's call it get. What should we call it? Get graphics family device queue. Get graphics family device queue. And it's going to care about. So basically, we're going to pull this out into this function and do the same thing, but for the present. So there's one for the graphics, one for the present queues. It's not particularly elegant, as they say in this, and that's correct. It's not, but hopefully it's going to work, and then we can figure out later on, if we care, to do some improvements on performance. Again, this is initialization. I don't think this section is going to be what holds up things too much. Okay, so inside this void, and it's going to need a whole bunch of stuff, such as, what does it need? It needs our indices. So it needs this, but it can just be a value, doesn't necessarily need to be a pointer, because it's not being saved anywhere, I don't think. No. I mean, it's not being saved on anything as a reference. So I'm just going to grab all of this. Oh, we also need the device features. All right, it's got our device features and we've got our instances. Let's pass them in. Sorry, indices and device features. Yep. And then let's just throw all this into, yeah. Oh, supposed to cut that or copy it. Cut copy. And let's double check that all works as we expect. Build. Nope, because I haven't got the app. Oh, I need to pass the app as well. Yes. Now then, what do we specifically want to reference for our app? But I don't need to pass the whole thing. I can just pass. Well, we need two things. I may as well pass the whole thing. App pointer to p-app. All right. So then in the calling of this function, there you go. Done. And then let's just basically the same thing again. Excuse me. I am literally going to copy paste that. And it's going to be for the present queue. Present. Queue family indices, present device, blah, 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 blah. Failed to create logical device. We don't need to do multiple logical device creations. No, we do not. I'm gonna have to figure this out. Properly. Okay. So these are independent of this. But that create info isn't. That's specific to graphics, is it? Is it? Is it? No, it's not. Undo all of my stupidity. The only bit we really need to break out is it? So if you've got multiple queue create infos, how do you do the VK create device with multiple queues? Well, with multiple create infos. To point to the vector. Oh, can that take? It is called infos. So okay, in this create info, which is for the device creation, the logical device creation, it can take multiple queue infos, right? So we initially passed in the address of this, but we could equally pass the address of the first element in an array of those create infos. That makes sense. So we actually need to just create multiples of this. Yeah. Okay. Yeah. I mean, sorry, this section here. So multiples of this is what we care about. All right. Get family device queues is the function I think we're going to create. Void. So that's going to contain, it's going to need our indices, I reckon. Indices and the device features. Yep. So let me throw that up there, along with our indices. From that, we should be able to create most of the stuff we care about here. Yep, I believe so. So this will be our graphics. And then we'll have to do one for present, queue, QUE, and then we also want to have a variable of a list of these, and we know the list is going to be 2, so let's just call it queues. Yeah, we know the length is going to be 2 because we've only got one for graphics and one for present. This would be where we do the optimization. Note, this would be where we optimize. No, optimize for performance. No, for single queue. Yeah, single queue index. I think that's kind of right. I think. All right, so in our queues, we have created our, this create queue info, this queue create info, sorry, is for specifically graphics. Graphics queue create info. And then we'll update just that here. Graphics queue create info. And then we'll do our return queues. And we'll say at position 1, well, 0, index 0, sorry, we are going to add this. I think that's probably fine. Then we'll just copy paste all that again, but we're going to rename it to present instead of graphics. Yep, it's not going to be graphics family. It's going to be present family. And I don't think we need to save the queue priority as its own variable. We can actually just, can we? Oh, let's just do this. Graphics queue priority. And then down here we have present queue priority. So that's the correct priorities. It's the correct families. And we're adding not the present, oh no. Yeah, we're adding the present queue, not the graphics queue info here. And then this should return not void, but in fact a pointer of those, not void. Oops. All right, so where that is called, we are expecting to get back one of these. So let's call it pointer to the first element in queues. And then we'll just pass our queues directly into here, I think. I don't know if we have to do a dereference or the first address. I think it already is the first address. I think that's right. We're not in this function. We haven't got any references to the app. So I think that's everything we need. Let's just try and compile it. Wrong thing. Build. Warning. Return queues. Function returns address of local variable. It does. What is that? Why is that a problem? Ah, we actually want to return the memory address? No. Ah, that's a good point. Let's accept the queues list and yeah, let's accept the queues list kind of in the same pattern that Vulkan does. Yeah, okay. It's a pointer to our queues, and then we'll just do this. Let's get rid of that note because I don't think it was super useful. And then it ends up not returning anything. And then, yeah, okay, so when we call on this function, which was here, we actually aren't doing this thing. We're creating our own queues, passing in the pointer to it. Whoops, I mean the address of it. Now, our own new set of problems. Passing argument 1 of GLW family queues. Excuse me. DK device create info queue, okay. Expected the pointer to the create info queues, but we actually got it's the same type, is it not? It should be a pointer. Right, what are we doing wrong? Lots and lots of things. My pointer knowledge is still not as good as I'd like it to be. Create logical device. Pass an argument, yep, for incompatible pointer. So we expected just a regular pointer to the device create info, but we were given a pointer to a pointer. That's fair. That's very fair. I don't know if that's actually visible to anyone. Now we expected a pointer and we received a pointer to a pointer again. We expected a pointer, we received a pointer to a pointer. Maybe we don't. Is that what I just did? Did I just compile that bit? Yeah. Okay. So I guess that's wrong. We've got a queue of a specific length. I need to refresh other areas that I'm doing this. Where else am I? Creating a list and blah blah blah. Yeah, just there, same sort of deal. Alright, so let's go back to that actually. How do we do that there? Const. So in these GLW extensions with debug, we didn't pass it anywhere to any function. Let's just pass it as is. It is a pointer. It's being passed into here. And we are accepting it as a pointer. And then in here we are assigning to it. Just notice that we're actually doing the wrong thing there. We're passing a pointer to a pointer in the function call. Are we? So before we put that in there, it was the pointer. Now it's pointer to pointer of that. Maybe. Surely we're not doing that. I'm a bit stumped here. This must be why some people are scared of C, I suppose. Let's take a look at the definition of some of these functions in Vulkan that accept an array of stuff. Let me scooch around and try and find an example. Here we go. We're creating an array. I've defined it incorrectly. That's the main problem. I've defined it incorrectly. I think that's probably better. Not amazing. Okay. But let's go back down to that definition that I was looking at. Let's go for vk enumerate. So in this function, let's find that in our Vulkan docs. So we're creating a list, or an array, sorry, not a list. And we're passing the address of that to this function. This function accepts the count and the available layers. We're not passing the address, we're just passing the thing itself, which is already a pointer. That's the point. It's already a pointer. Remember this. Yes, when we create an array, the type of that is the pointer to the first element because it's an array. So then if we pass that by reference to a function. We don't need to add an ampersand to the address because it already is that. Right, I think this will probably compile now, and it does. All the time we're learning, it just sometimes is a little bit slow. All right, so now we've got our two present our present family and our graphics queue family. We've got those two, and we are creating our device, but are we actually using it properly? Here's our queues. Yep, we're passing in both of our queues to the create info struct, which is used to create the logical device. Fantastic. And let's just try running it. So let's see what happens. Things are fine, things work, things are great. Life is good. All right, we finished that little chapter. That was not so painful. In the case, the queue families are the same. Yeah, that's fine, we already read that. In the next chapter, we're going to look at swap chains and how they give us the ability to present images to the surface. That's gonna be so good. Okay, until then, thanks, see ya.